All right, so this is going to be our second set of PowerPoints. This chapter is going to focus on energy, how we treat energy, and then go into specific heat, and then we're going to be looking at changes of state and matter in general. So we're going to finally, towards the end of this lesson set, get into chemistry a bit as we talk about matter. Again, I'll try to keep these chunks down to about 15 minutes or so, and I'll try to find good stop points where, in class actually, that's where we would probably take a break if we were face to face. So in this chapter, like I said, we're going to talk about general pieces of energy. We'll look at energy and nutrition. We'll look at temperature conversions, and we'll look at specific heat. And there's that word conversions again. You can see that's not going to go anywhere anytime soon. We're constantly doing conversions, as we spoke about in the first chunks that we looked at when we talked about problem solving. So energy. What is energy? Well, energy is the ability to do work. So that means that you need energy to get things done, and we know that without even thinking about the math behind this. The definition of work is to cause a change or move an object. So if you're having one of those days where it was just work getting out of bed today, it really was work to get out of bed because you had to move yourself out of the bed, and that cost energy. Now, we're not going to get into the details of energy and all the different things, but there are some things about energy we have to know. For instance, there are many different types of energy, and they can change from one form to the other. In fact, that's our whole world. If you really stop and think about how your world works, you get up in the morning, you probably get some breakfast or at least a cup of joe, got to get some coffee in you, and then you start to do things. Well, that coffee or that breakfast is your fuel. And so it goes all the way through into the mechanics of all the things around us. So what types of energy are there? Well, the first things we see are two big umbrella types. So all energy has to fit into one of these two categories. The first type is potential, which is stored energy. So this is energy that hasn't been used yet. So it's like a battery. That's potential energy. The energy's in the battery. It's waiting to be used. And then the second type would be kinetic, and this is the energy of something that's moving. So now we're taking those electrons that are in the battery, we're actually flowing them across the wire, and we're doing work. So that's the type of energy that we have. It's either going to be potential or it's going to be kinetic. Now, here's where it gets a little confusing because we're using the same vernacular. We're saying the types of energy, but if you want to think about it, we have two categories. We have potential and kinetic, and now we're going to have a whole list of types. And the first type we're going to be looking at is going to be heat. Heat is the one that we actually focus on in this course, so we're only going to be looking at temperature change. So as changes of temperature take place, we can see where the heat is moving, and that's going to be a form of energy. Another form of energy would be chemical energy. Now here it's going to be presumed, but we're not going to actually get into the nitty-gritty of it all. We're going to look at the nitty-gritty of heat, but we're not going to look at the nitty-gritty of chemical energy, which is kind of strange since it's a chemistry course. But it actually takes quite a bit of math to get into the energy focus here. Typically, you have to get into some higher order algebra, technically even into calculus, but usually what we do is we introduce the calculus in chemistry courses and then reduce it down to the algebraic formulas. Here we're not even going to get into that, so we're not going to worry too much about the details here, but we will look at the release of energy because we'll talk about heat release, we'll talk about light being released, and these are forms of chemical energy that are being released and changed into other types of energy, i.e. spectral chemistry and heat chemistry. There's electrical energy. So this is the energy of moving charges. And of course, we'll touch on this because we talk about the charges of the different particles within the atom. So we have atoms are going to be made up of protons, neutrons, and electrons. And it's not assumed that you know that walking into the course. We'll actually visit those concepts in the next chapters. So here, what we're going to be looking at is just the idea that an electron can flow across a wire. That would be electrical energy. Radiant energy, and this is probably the most common in our world actually. This is light, UV, infrared, radio. If you're a cell phone user, right, that's your radio energy, a radio signal. So that's going to be radiant energy. Now, again, as I said earlier, all types of energy can be converted from one into the other, and that is including potential and kinetic. So I can take potential energy, turn it into kinetic energy. I can take electrical energy and turn that into radiant energy. We could take radiant energy and turn that into a sound energy, right? So that's directly using your cell phone. So you might receive a phone call that started as a radio wave that was coming down as radiant energy. You then turn it into sound energy, which then goes into your ear, and then you can process that information. All right. Now, if you trace the source of all of our energy back far enough, you end up at nuclear energy. And of course, there we're talking about the sun. Okay, so nuclear reactions take place on the sun. The sun then produces radiant energy, which we here on Earth absorb as heat and UV. That causes the plants to grow, which eventually becomes our food, which then allows us to do work. So, in a very generic sense, that's the chain of energy flow. Now, obviously, you want to get into the nitty gritties of it all, the math can get extensive, and we won't worry about that. Here you can just trust Mr. Caro if you want, or you can do some investigation on your own, and if you have questions, feel free to shoot those to me. But at the end of the day, what we have is the conservation of energy. So energy can be neither created nor destroyed in ordinary changes. Now here, look at that in the parentheses, not nuclear. And this course is not really designed to get into the nuclear components of this. So we're going to talk about atomic structure, but we're not really going to get into nuclear energy, into like the nitty gritties of it all again, because again, it's going to be high order math, and we just need to get a general sense of how the chemistry is going to play out. Now, this is also considered a law, so it's the law of conservation of energy. If you took the time to peruse chapter 1 of your textbook, they would have talked about the scientific method, and there you would have seen how it becomes a law. So there's a difference between scientific law and scientific theories. And if you have questions about that, again, visit me, check out one of our student hours, or check with your tutor, or send me an email. I'd be more than happy to go into more depth there. Along with the conservation of energy, there's also the conservation of mass. So mass cannot be created nor destroyed in ordinary, again, not nuclear changes. So that means all of our mass has to be accounted for. So I keep saying, what about nuclear? What about nuclear? Non-nuclear? This can't be nuclear. It's only true when it's not nuclear. So what makes it special? Well, that was that little famous equation, E equals mc squared. Most of us probably recognize this from science courses somewhere, where Albert Einstein he's noted for this equation. It's one of his most popular equations. Mathematically, what he's saying is energy is equal to your mass times the speed of light squared. So if you've ever wondered why you struggle to lose weight like I do, well, it's because you can't run at the speed of light. That's right, I paused for the joke because I was just kidding. I hope you guys are laughing at that. It's not quite true when it comes to us losing weight. There's some biological processes that go on there as well. But the point is, if you have just a little bit of mass, you can make a whole lot of energy. And so that's how we take advantage of that when we look at nuclear reactors. So we use a nuclear reactor to generate a lot of energy for a really, really small fragment of mass. Now, if I really want to include nuclear into all of this and still have some sort of conservation law, which we do, it's called the law of conservation of mass and energy. So here, the total mass and the total energy have to remain the same throughout any possible change. All right, and again, we're not going to get into major details here. That's just an overview of energy, potential versus kinetic, and then the different types. We'll be focusing on heat. Now, what I want to do then is make sure you do know the difference between potential and kinetic energy, though. So we're going to play a little game called Name That Energy. So I'm going to bring up a topic like climbing, and at this point you need to decide in your mind, because I can't hear you, of course, if you believe that is potential or if that is kinetic. And of course, that one is kinetic. How about jumping? Jumping, potential or kinetic? Well, if you're in the motion of jumping, then it must be kinetic. How about sitting? Well, if you're sitting, then you're not doing anything, you're not moving. That means you have potential. How about running? Running again would be kinetic, you're moving. How about a spring? Oh, what type of spring? That would be a good question, because is it a water spring? That would be kinetic. Is it a metal spring that's just a coil sitting there? Well, that could potentially be potential. So if it was a compressed spring, so a metal coil spring that we've now compressed down, that is kinetic, correct? No, potential. Oh no, I'm confusing you. No, seriously though, a compressed spring would be potential energy. So if it was not compressed, then it would be potential as well because you have to squeeze it down. But if you release it and let it, I don't know what you call that, let the spring be sprung, then that would be kinetic. Now, the reason why I bring up springs is because what about a chemical bond? And if you're an older student like myself, when I first started into chemistry in high school, we used wooden balls with metal springs as bonds. And so that quickly could tell you that a chemical bond is going to be kinetic when it breaks, potential when it's made. So when we make a bond, that bond then, it's like a battery waiting to be used and let that charge go. So when we break the bond, we'll get energy in that. Okay, so bonds then are potential sources of energy. In fact, our bodies will store that energy in bonds, and hopefully your A&P prof will get into that a little bit in more detail. Now, heat energy then, which is what we're going to be focusing on, is the heat that's measured in joules or calories. So got a few pieces here we have to kind of tuck away. You might want to write it down somewhere. You'll probably need this for different types of assessments. But 4.184 joules is equal to 1 calorie. Now, that's not a food calorie. That's a heat calorie. And I mentioned before when we talked about the metric system, the 4.184 joules is a metric unit. So this conversion is a little bit weird because it's not a base 10, but we're going from joules to calories. And of course, this is an exact value, so it won't impact your significant figures. However, if we apply metric systems to this, which is what we will do, we'll get kilojoules. Simply means we have 1,000 joules. We do the same thing with calorie. We can have a kilocalorie, 1 kcal, will equal 1,000 calories. So again, there is some exchange there. They're both metric units. There is this first odd conversion though, and you will have questions that ask you to convert from calories to joules and joules to calories and things of that nature. So you want to be prepared and have that written down somewhere, or have it, I don't want to say memorize it. I'm not a big fan of memorization. I'm a bigger fan of being able to apply it. All right, so some common energies in joules. You don't need to memorize any of these. I typically put this in here so when we're in a live class, we can talk a little bit about this unit because a lot of us are not familiar with heat units. So we're not used to joules, we're not used to calories, we don't understand their magnitude. It's not like I said, oh, let's go out and run a mile. You have an idea of how big a mile is, right? But you might not have any idea of exactly how much energy would say be in a gallon of gasoline. So in 1 gallon of gasoline, it's 10 to the 8th joules. So you can see the joule then as a really, really, really small unit. And when we talk about calories, a lot of us might say, okay, well, I understand food calories. I'm allowed to have approximately 2,000 calories a day, Mr. Carroll. I understand that. Well, like I said, it's not a food calorie that we're talking about. It's a heat calorie. Now, we will see later there is a relationship between those two, but it's not an exact. And so hopefully, once we talk about food calories a little bit, maybe you'll get a good understanding of these units as well. Now, how do we keep track of that? Well, we said that what we're going to be focusing on is the heat of the energy and nutrition. So when we look at nutrition, what we have to do then is figure out what the heat transfer is. It's really hard to measure heat, but it's easy to measure temperature. And the temperature is related to the heat, right? It's going to take heat to heat something up. To make the temperature increase, I have to give it heat. So what we can do then is measure temperature change, and then we can relate that to heat. So what we do is we use what's called a calorimeter. So this little coffee cup device is called a calorimeter. And what we'll do is take some styrofoam coffee cups. We'll take 2 of them usually. You inlay them together, and then we put some water in here. Now we have to know how much water is here, right? Because if I have a gallon of water, it's going to take more heat to heat up a gallon than it's going to take to heat up a quart. And hopefully that makes sense. That's not even a chemistry principle, right? That's a life principle. If I want to boil water in order to make something in my kitchen, if I use a bigger pot, it's going to take longer because I have more water in it, right? So it's the same principles here, except we'll be able to put numbers to it. Now what we want to do is measure that temperature change for the water. And of course, we're going to want to stir that water so that the heat goes through it evenly. Now what we can do is heat up, in this case we're using a piece of metal, a sample metal, and we're going to heat that metal up, and then we're going to put it in the coffee cup, and what's going to happen? Well, the heat is going to transfer from the metal to the water. And so when that happens, we'll be able to see a temperature change, right? So as the heat transfers from the metal to the water, we'll be able to measure that change in heat. So that's what we're doing with a calorimeter. We're measuring the heat that's being changed, and then we're going to convert that unit into calories. Hence calorimeter. It's measuring calories. Now, again, we'll make this with a coffee cup, but if I wanted to get into like the food business, like if I wanted to be, part of the Hers family and I wanted to look at potato chips and I wanted to produce that label on the back to tell you how many calories it is, I'm probably not going to use a thermo cup, right? In fact, what I'm going to use is called a bomb calorimeter. And that's an expensive instrument. They range, not that it's a big deal to you all, but $5,000 to $20,000, depending on how good of an instrument you want. And that's where it comes back into play, right? It costs money to have good instruments, but good instruments make better measurements. Okay, so our measurement device here, it's not going to be the best measuring device. There's going to be a little bit of error, but believe it or not, in some of the experiments that we would run using especially the metals, we can get really accurate numbers. So we don't need to put a whole lot of money in necessarily to get good data. It really depends what we're measuring. Now, if you want to know the calories of a sour cream and onion potato chip, this isn't going to work, all right? What am I going to do? I'm going to heat that potato chip up. I'm going to catch it on fire maybe, trying to heat it up, and it's going to burn, and somehow I have to capture that heat. So there are ways to do it, but it's going to be more easily done in the right instrument. So again, what we'll be looking at here is the heat being lost by a sample and gained by the water, all right? So again, we're kind of leading this into nutrition. And so I said there would be a relationship between that little calorie and a food calorie. And I think we'll end with this on this chunk. So here's our piece here that's going to relate to that. And notice the differences here. I said in a previous chunk when we talked about units, I said case matters. And here it is. Here we have a capital C, CAL. So we have a large C for calorie. That's a food calorie. Whereas when we have a little c, that's going to be our heat calorie. And here we can see that one food calorie is going to equal 1,000 of those little calories. And so that's going to be our conversion for that. Again, I'm not going to expect you to memorize these conversions. You'll have them at your disposal when you go to do different assessments, whether it's a writing assessment or a test or a quiz or whatever it will be. Make sure you have these sheets available to you. You can even jot these down on one piece of paper, and that way you'll have that. I believe in D2L, I've provided a sample sheet of practice stuff that you can use. So a lot of these conversions might be on there as well. And if not, you can just add to it, add the ones you think you might need. All right, so I'm going to sign off here for this chunk, and then we'll break the chapter down into a little bit more. So we'll talk a little bit more about calories, and then we'll look at that what's called specific heat and how we can take those temperature changes and change them into the actual unit of heat. All right, so stay tuned.